This is the 11th session of the Decision Tree series, and our third session on cost complexity pruning. In the previous two videos, we covered the theory behind cost complexity pruning. In this video, we will put that theory into practice and implement it in code. Now, we will walk through a code example from the scikit-learn documentation shown on this page to understand each step in detail. We construct a full decision tree that perfectly fits the Titanic dataset. Then, we apply cost complexity pruning to simplify the tree and improve its generalization performance. Instead of implementing this process from scratch, we will use scikit-learn's DecisionTreeClassifier to do this easily. Let's start by loading the Titanic dataset and performing basic pre-processing. The dataset consists of 7 features and 1 target variable. Since it includes several categorical features, we apply label encoding to convert them into numerical values. As mentioned earlier, decision trees do not require feature standardization, unlike many other machine learning models. For this reason, we do not apply feature standardization here. Next, we split the data into input features X and target Y, and then divide it into training and test sets. We then create an instance of the DecisionTreeClassifier to build our tree model. Next, we call the cost complexity pruning path function using the training data. This function returns 2 lists: the effective alpha values and the total impurity of the leaves for each subtree. We can use these lists to determine the optimal level of pruning. The effective alpha list contains the alpha star values of the weakest links that we discussed in the previous video. The impurity list contains the misclassification rate of each subtree, denoted as RT, as defined earlier. The last value in the effective alpha list corresponds to a tree where all branches have been removed, leaving only the root node. In other words, this represents the most heavily pruned version of the tree. However, since this tree is not very useful in practice, we typically exclude this final value when selecting the optimal alpha. The same applies to the impurity values. As alpha increases, stronger pruning is applied to the tree. This makes the tree simpler by reducing the number of leaf nodes. However, this increased simplicity comes at a cost. The model may lose some of its predictive power. As a result, both impurity and misclassification rates tend to increase as pruning becomes more aggressive. In this example, we obtained 71 effective alpha values. This means that there are 71 weakest links in the fully grown tree, and each of them is pruned to generate 71 candidate subtrees. Our goal is to select the best performing tree among these candidates. Next, let's visualize how impurity changes as alpha increases. As expected, you can see that the impurity increases as the alpha value increases. Again, as alpha increases, more pruning is applied. As a result, the tree becomes simpler, impurity increases, and accuracy decreases. Next, we create multiple decision tree models, one for each alpha value in the effective alpha list. We fit each model to the training data, and store it in a list of models. Then we measure the total number of nodes in each tree, as well as the depth of each tree. Next, we examine how both the number of nodes and the tree depth change as the alpha value increases. As expected, both decrease steadily as alpha increases. Let's also look at the number of split nodes, which are the non-terminal nodes of the tree. At the very bottom of the tree are the leaf nodes, which represent the final outcomes. The nodes above them are called split nodes because they divide the data into smaller subsets. In this example, the fully grown tree contains 165 split nodes. However, only 71 candidate trees are actually evaluated during the pruning process, not 165. This is because 71 of the 165 split nodes correspond to the weakest links in the tree. Since it is not necessary to evaluate all 165 split nodes, cost complexity pruning can be performed efficiently by focusing only on the candidate subtrees. For example, if this split node is identified as the weakest link, we prune the tree at this point. As a result, the nodes below it are no longer evaluated, since they are removed during pruning. For reference, in a binary tree, the number of internal nodes is equal to the number of leaf nodes minus 1. Since this tree has 166 leaf nodes, it has 165 internal nodes, which matches our observation. Next, we evaluate each model to measure its performance. We compute accuracy score on both the training and test sets. Then, we select the alpha value that gives the highest test accuracy. The tree corresponding to this alpha value is our optimal model. Next, let's visualize how accuracy changes as the alpha value increases. In this plot, the blue line represents training accuracy, and the orange line represents test accuracy. When alpha is 0, meaning no pruning at all, training accuracy is 100%. But test accuracy is only around 80%. That's a clear sign of overfitting. As alpha increases, training accuracy gradually decreases, while test accuracy increases. This happens because pruning reduces overfitting and improves generalization. At a certain point, test accuracy reaches its maximum. After that, it starts to decrease again as the model becomes too simple. The model at this peak is our optimal choice. Finally, we evaluate the selected optimal model. Training accuracy comes in at around 88%, and test accuracy at around 85.6%. Now let's run this code. The results are consistent with what we observed in the previous slides. To summarize, in this video, we implemented cost complexity pruning on the Titanic dataset and saw how selecting the optimal alpha value helps balance model complexity and generalization performance. In the next video, we will move on to multi-class classification. See you in the next video.